All right, perfect. Thank you, Sakshi, for the nice introduction. And it's always a pleasure to have this opportunity to present this OPTICA Technology Showcase. So I am Valentin Genuer, and I'm field application specialist at Phasics. And today I wanted to present you our latest innovations in terms of optics metrology, and in particular, I would say wavefront or metrology of optical system at their design wavelengths. And from the features you can see here, the focus will be on applications such as free space optical communication and autonomous car. So for my presentation, I will first go back quickly on Phasics, who we are, what we do in optics metrology, and then focus on two of our latest innovations in optics metrology. So Phasics, what we do, our core competencies are wavefront measurements and making high resolution wavefront sensors and integrated test stations for optics metrology, beam testing, beam characterization, having the optical aberrations of an optical system, doing optical alignments, and full characterization of optical systems. So everything, all of our solutions rely on our patented technology, which is quadri-wave lateral shearing interferometry. And at the beginning, Phasics, it's a spin-off between two French laboratories. And we are established since 2003, and all the production and R&D is in Paris, in France. And I work for the US branch of Phasics, which is based in San Francisco, California. To support our clients worldwide, we have a strong network as well of distributors in Asia and in Europe as well to, as I said, support our strong, I would say, clients worldwide. So what kind of solutions can we provide at Phasics? So we are a leading expert in, as I said, compact wavefront sensing, and we offer different types of solutions depending on the needs to do transmitted wavefront or reflected wavefront or MTF, so modulation transfer function, having the lens parameters of an optical system. And basically we do this from the UV to the long wave infrared range, depending on the type of system integrates. The first type of solutions that we can provide are standalone wavefront sensors, basically a wavefront sensor that you can integrate in your own test bench. You have to build yourself a test bench or simply place the wavefront sensor in your laser system to be able to do the wavefront measurements. We also provide software delivering kits so that you can integrate the measurement in your own code or interface. And you have the flexibility to move the wavefront sensor wherever you want and apply it to the project you want. The second type of solution is a step further in terms of integration, where we would provide still the wavefront sensor package, but also beam shaping elements such as beam reducer, beam expander, as well as sources like qualified and fully characterized sources, so that you can assemble the different elements yourself and build a test bench still yourself, but you still have the flexibility of using the different elements, swapping the beam expander for a 5-inch beam expander to, for example, a 1-inch beam expander, still use the wavefront sensor as a standalone sensor head in your optical system, but it's a step further in terms of integration. And then the last type of solution is where we specialize in as well, is designing custom and fully integrated test stations to do optics testing. So basically it comes from single like R&D oriented test bench, still modular, that you have for low volume production and R&D with an expert software, be able to do multiple testing to a very fixed and specific application, a machine fully integrated that you will find on the workshop floor, operated by the technician. And we span very, like I would say, all the solutions from just the standalone sensor to the fully integrated test stations. So if I go back on what we presented at the last technology showcase, it was about a challenge that we see more and more in optics metrology, where we see more and more lenses having very high Chiffre angle. And even sometimes Chiffre angle is nonlinear across the field of view of the optical system. And that comes as a challenge of the current optics metrology standard instruments that you can find the MTF test bench. So we decided to upgrade our existing MTF and wavefront machine to be able to handle this kind of very complex lenses and still be able to provide very accurate wavefront or MTF on and off axis of lenses having a very high CRA, so Chiffre angle, even above 35 degrees and even more. And even when the Chiffre angle is, as I said, non-linear across the field of view. So this type of machine provide MTF at multiple wavelengths, wavefront aberrations. If the pupil is circular, it will provide the Zonicky polynomials, and as well as classical geometric and radiometric lens parameters, such as the focal length or distortions and so on, and relative illumination and so on. But today, I really wanted to focus on this test bench that our engineers worked on for the past years, and that come to solve two main challenges that we see more and more in optics metrology today. As first, the measurements and the qualification of an optical system at its design and working wavelengths. And secondly is to be able to measure high wavelength or amplitudes. So the first challenge is because we wanted the optics community to be aware that solution exists to actually characterize an optical system at its design wavelengths. It makes, I would say, little sense to now measure an optical system using a standard piezo interferometer at 633 if the final optical system application is to work at 940 nanometers or 1550 nanometers, even if the optical system is able to transmit at 633, because sometimes you can apply coatings that will prevent to make the measurements of the final optical system. And so we wanted to make sure that the community know that there are solutions, very robust and accurate solutions that are able to provide the metrology of optical components at virtually any wavelengths from the UV to the long-wave infrared range. And basically, this type of optical system so integrates our high-resolution wavefront sensors, and the key features are, as I said, being able to make wavefront or transmitted wavefront or reflected wavefront or measurements at multiple wavelengths within the same test bench. I would say it's like having a piezo interferometer at multiple wavelengths. So you spare the cost of asking known manufacturer of piezo interferometer to build you a specific interferometer at the dedicated wavelengths, because it's still expensive today to have an interferometer working at 1550, for example. And here it's a good alternative in terms of wavelengths flexibility to have this kind of test bench here. And the second thing is being able to measure large wavefront or amplitudes without having to use null testing solutions like computer generated holograms, for example. So here the test bench is still able to provide very accurate measurements, even when the system itself is generating large wavefront or amplitude, like I'm speaking about tens of microns of sag or curvature, for example. And that can arise in a lot of optical systems that we see in different applications today. And the last thing is that this kind of test bench, we have off-the-shelf test bench with fixed pupils, but there are still flexibility in terms of customization, because we can adapt the pupil size from a 5-inch, like the test bench you see here, pupil to a smaller pupil. We can adapt the source as well that we integrate in the test bench if we need to use LEDs or laser, or in the infrared range, QCL, ICL, or even further like black bodies in the long wave band, or CO2 lasers, for example. And we can adapt as well the orientation of the output pupil. Let's say you need to integrate this type of test bench in a production environment, and you want to have the beam coming upwards to measure filters or optical systems that are coming on a tray. This is totally doable, and this is what we specialize in. And the key applications and markets we see for this type of test bench are first, free space optical communication with the measurement of transmitted wavefront and reflected wavefront of narrowband filters in the shortwave infrared range. And the last thing is autonomous car, as I said at the beginning. So being able to measure, again, wavefront error of optical system of windows for integration in LIDAR systems, and then further being able to characterize the integration of a LIDAR in a car by being able to measure windshields, very curved optics such as headlight optics, and still be able to measure very high phase gradients in terms of wavefront measurements. So I think that's what I wanted to present today. So again, we cover a wide range of applications from consumer electronics, smartphone, or AR, VR, MR systems to LIDAR systems or astronomical application. We cover a wide range of application, and thank you for your attention.
Thanks, Valentin. Great presentation. So it looks like there is a question here from Giles. He says, do you need reflected wavefront for smartphone camera module applications?
So I'm not sure I understand the question, but basically for, I would say smartphone module, basically will not measure the full camera module, will measure the optical system itself. And then for the integration of the optical system with the sensor, this is not what we will do. We will provide only the measurement of only the lenses, the optical system, not the full camera module, so lens and sensor. So basically we provide the measurement in transmission for the optical system.
Okay, and another question here is, what wavelength range and pupil size do you offer?
So in terms of wavelength range, so basically we will cover the UV, so from 193 nanometers up to the long wave infrared range, so 14 micron. It will depend basically on the sensor and detector array that we will integrate. So from CCD detector, like silicon detectors for the visible range, with in-gas sensor in the infrared range, up to microbolometers in the long wave infrared range. And for pupil sizes, it will basically depend on the optical system you want to test. So from the size of the sensor itself, which is few millimeters, up to 5-inch or 6 inches. It will really depend on the type of optical system you need to measure.
Okay. And another question I'm seeing here is, what are the differences with a standard interferometer?
So the main difference is that in our test bench, we integrate the wavefront sensor. So the wavefront sensor is making the wavefront measurement. And compared to a traditional interferometer, a wavefront sensor measures the phase gradients, which means that we measure the derivatives of the phase, which means that intrinsically the technology has more wavefront error amplitude and dynamic range, since we measure the slope of the wavefront and not like an interferometer, directly the phase. And basically another advantage would be that the wavefront sensor itself, since it is self-referenced, it's not sensitive to vibrations as well. So you don't need to use phase shifting interferometers to prevent from vibrations to, I would say, impeach you from making the measurements. Basically here, the wavefront sensor is very much more robust because everything happens in the camera. The wavefront measurement happens here, so you can integrate it in production lines. It's way more robust. And the last thing is I can add is that the technology itself is achromatic, which means with an interferometer you have one fixed wavelength in the test bench. Here, the technology that we have is fully achromatic, which means that there is no need for recalibration. If you change the wavelengths of the tests, can measure the performances are the same across the sensitivity range of the detector.
Great. Well, thank you so much, Valentin, and thank you for presenting on behalf of Phasics.